Welcome to WasmAssembly episode 11. This is a very special episode because it's the first one where I have not just one guest, but two. Welcome Mendy Berger and Sean Isom, both from a company called renderlet.
Welcome. Thanks for having us, Tom.
Hi, Tom.
Hi, Mendy. Great to have you. Renderlet, if you go to the homepage, the punchline of the homepage says, write graphics code once, automatically run on any platform. So this already hints at WebAssembly. And renderlet is indeed a WebAssembly framework for writing graphics code actually that runs anywhere. This means that developers can use renderlet to embed GPU-accelerated 2D and 3D graphics into cross-platform applications. But what actually is renderlet? So Sean, maybe you as the CEO, can you just shine some light? What is renderlet?
All great questions. I would sum it up as renderlet is a plugged-in framework for GPUs. And so if you kind of look at how graphics are built or graphically intensive applications are built, you have code that runs on the CPU. And so that often is written against a graphics API, something like OpenGL. And the goal of that is effectively to configure the GPU, to put data on it and issue instructions to render graphics. And then you've got GPU side code as well, and these are known as shaders in the graphics land. You also have things like CUDA, which is very popular for machine learning, scientific computing. And so kind of this nexus between the CPU and the GPU represents how graphics are rendered onto a screen. And so if you look at WebAssembly, it is the perfect framework for compartmentalizing and componentizing code that runs on the CPU. And so what renderlet can do is it can provide that GPU to WebAssembly code and provide that interface, and then back that with WebGPU, which is a safe backend. And we'll get into the details of WebGPU, I'm sure, but it's a safe backend for running cross-platform graphics code. It does things like shaders, bound checks, etc., to ensure that we can do safe cross-platform GPU computation. And so it's kind of a nexus between those two technologies to allow us to build a fully componentized rendering system. So renderlet takes a kind of a data-driven spec of the graphics pipeline. Here's your buffers, here's your data, here's the operations we want to perform, here's how we order them and put them on the screen. We generate a bunch of CPU side code in WebAssembly to configure a graphics pipeline, and then we use WebGPU on the back end to render the graphics. And so the goal is to kind of build this self-contained plug-in system for graphics. I'll use an analogy. Let's say you're writing code with Node.js and you're used to just grabbing a library from npm. If you're trying to build a game, or if you're trying to build, some sort of visualization for CAD or something, there's not that same analog where you can just grab an off-the-shelf component and put it in your application and just have it work and render data to the screen. So that's the goal renderlet wants to work towards, is providing this kind of componentized rendering system. Right now, we're kind of investing very heavily in building a graphics editor. It's still closed preview. We're not quite to a public release with that. And we're experimenting a lot with kind of procedural graphics and all these different technologies that make it easy for people to build these really awesome effects.
So there's been a lot of specialized terms that I will ask you about in the next couple of minutes. But before we go there, just very briefly, renderlet, it's a startup, I guess. So Sean, you're the CEO. Mendy, you're the head developer, I guess. How do you distribute work? Is there more people? Sean, I think you're also still very heavily involved in the coding. How do you structure, person-wise, the renderlet company?
Good question. And I'll defer some to Mendy as well, because Mendy is our expert developer, but I still spend probably the majority of my time writing code too. I mean, we're a small company. We're 3 people, some help from contractors. So you're talking to two of the 3 of us. Myself, I used to work at Adobe for years before. That's my background is in C++ and distributed systems. I have been handling more of the graphics kernel aspects. I've been working on a lot of the really math and rendering code and stuff behind the 3D engine. Marianne, who's not here on the call, is our head of design and is really helping us think through our user interaction strategies as we build our app. And Mendy is our resident Rust and Wasm expert, and I'll let him talk more about what he does.
Yeah, so I focus on the Wasm side of things. yeah, there are two parts to this project, which is like graphics and Wasm, and Sean is doing most of the graphics side, and I'm focusing more on the Wasm side. And I guess Rust. I I I am more comfortable with Rust than Sean, I think, but that's changing quickly.
All right. So Sean, you worked at Adobe before. You said Adobe is a big Wasm user with Adobe Photoshop on the web. Were you involved at all in this project?
Not really. On the sidelines, I knew some of the people that were working on it. As I was kind of working with some of the core Wasm technologies deployed across Adobe at the same time. But when it finally, I think, hit beta, I want to say, was that 2022? I remember right, that was 2022. Like the entire company was thrilled to see the potential of this and watch it roll out across the platform and kind of see the gears turning because if you look at how Adobe had kind of internally structured some of this, this was a 10-year plus journey. It wasn't just Photoshop with WebAssembly on the web. It was kind of a rethink of how do we take our products and ship them in a different form factor, make them accessible to more users, make them easier to onboard to, and just kind of bring all the benefits of the web platform to it. So I wasn't directly involved in that, but I was kind of on the sidelines, working with Wasm at the same time, and working on platforms that enabled these to push to all of our different apps.
Makes
Well,
sense. Makes sense.
someday. I'm not sure they're there yet, but that's clearly the direction they're going.
Hmm. Yeah, I definitely remember. I was mind blown when I first saw the demo, and it's like, whoa. I always used to say, yeah, you're like building Photoshop or something. That's like the metaphor for the completely impossible app to build on the web, and then Adobe did it. So, yeah. Anyways, just wanted to very quickly catch up on your background there. We will talk about Adobe and other apps like that, Photoshop, in the next couple of minutes. But you both gave a talk at WasmIO last year and introduced renderlet. You spoke at WasmCon as well, and I just heard you will speak at the upcoming WasmIO in Barcelona again. So there's a lot of talks, and will be a bunch of talks that you can catch up with if you're interested. We will link the one talk that I have taken as the structure for this overall podcast episode in the show notes, so you can catch up and see the slides and everything. But just for the audience, can you just briefly summarize what did you present in this talk? How does renderlet work? What problems does it solve, and so on? And yeah, so just take it from there.
Definitely. It's crazy to think that that talk was almost a year ago now because a lot has stayed the same, but a lot has also changed since then. And it has part of the journey of being on a startup is it feels like it was yesterday. It's all kind of a blur. Um,
Well, in big corporations too. So my job is definitely like, oh my god, so many
very
things
very
changed.
true. That's the nature of technology and the nature of society, right?
It's the industry, I guess.
Yeah. Looking back at it, this was kind of in the very early stages of Renderlet, and that talk specifically actually predates Renderlet being a company, where we were presenting a library called Wander, which is kind of a abbreviation of WebAssembly renderer. And so the background there and how I got started with all of this was very simply saying, how do we bring GPU technology to Wasm? And if you think about how Wasm works in a web browser, obviously there's JavaScript bindings to many different parts of the web. And so you can do things like WebGL and WebGPU and hit there's other APIs as well, plenty of other web APIs that you can hit through JavaScript bindings, through tools like Emscripten. But if you look at kind of the proliferation of WebAssembly outside of web browsers, kind of initially function as a service type stuff, but moving into even things like desktop apps and plugin systems, there's you have to go through something called WASI or provide custom guest host bindings to provide some of those system capabilities that are provided by browsers out of the box. And so very, very simply, this idea started with, cool, we have Wasm running everywhere. How do we hook up GPUs to Wasm? And that led to a library called Wander that I wrote, which was it's a little C++ interface that works across, I think, 3 or 4 different GPU backends that provides a small subset of those functions, and no asynchronous operations and no back and forth. It's more just like produce data in the Wasm side and get it onto the GPU on the host side. Um, kind of logic. But it was a good way to very quickly bring GPU support to Wasm guests. So that was kind of the thesis of the talk, was presenting Wonder, looking at some of the background behind this and saying, like, why do we want to do this, and introducing kind of some of these concepts that I talked about at the very beginning of this, with the component-based rendering and being able to kind of like package graphical components as libraries that people can use. So, and I think the last point I'd touch on from that is, as I've been building all of this, and as others in the community have been working towards GPU things in Wasm, and just working on uh, distributed GPU applications in the first place, it's clear that we have a DevX problem. Um, you can't take graphics code that's kind of embedded in one application that's very low level and make it work inside another application really at all. You're often just kind of rewriting a lot of that code. Um, Getting it cross-platform is possible with certain frameworks and certain libraries, but making that work truly cross-application is almost impossible. I think game engines have kind of gone down this path a little bit. Like, you look at something like Unreal, it's got plugins. So like, if you stay within their ecosystem, there are ways to do this with guardrails. But I wanted to do something a little bit different, a little bit bigger, which is like, how do we solve this problem globally and enable rendering for all of these different things in a platform agnostic, technology agnostic way. Um, so that's kind of the background of the talk. I think at the very end of the talk, I teased what ended up becoming what all the stuff Mendy and I have done over the last year, which was we wanted to retool on top of WebGPU, because at the time I was writing these graphical backends myself. Um, and this way we get multiple platforms and we get much higher feature level support than Wander ever had. And so since then, it's not that we have deprioritized Wonder, but we've really been putting all of our efforts into the WASI WebGPU backend, which Mendy will talk more about, and the wasi-gfx project in general, into kind of retooling renderlet fully on top of it. So we'll still support Wonder, we'll still support all the concepts we did in that talk, but what we're building right now is kind of a superset of that, where we can actually do things like generate shaders in the Wasm guests and push those onto the host, and give you the full rich GPU ecosystem that exists.
Yeah, so
Long answer.
you mentioned a lot of things here, and I have to disclose I'm not a GPU, not a graphics expert at all. You mentioned procedural graphics. You mentioned game engines. You mentioned libraries. So thinking about the things that I sort of there's Three.js, for example, which allows you to talk to the GPU. So all of those different libraries, tools, content creation tools, game engines, sort of deal with the same problem, which is eventually getting pixels onto a screen or onto a canvas. But like many, in just a relatively short answer and summary, what is the difference to what is already out there?
Okay, that's a really good question. Let's think of it like this. In terms of how you represent graphics, they're typically represented in 3D applications as polygons, and even in 2D applications to some extent. And so the very short version of a round trip through the graphics pipeline, which is a great series, you should read that, I'll put in the show notes, is a developer will take vertex data, they'll take 3D points, and they'll take edges that connect those into polygons. They will upload those to a GPU just as a buffer. They will attach something called a shader, which is just a little program that runs that tells the GPU, okay, I've got this input data. Here is how I turn that input data into pictures that go onto the screen. And so if you look at how a lot of applications are structured, this is a gross oversimplification. There's a lot more than just this, but this is kind of the building blocks. If you look at how applications are structured, they will take, they'll take like 3D model, they'll take something like a GLTF, and they will upload that to the vertices from that to the GPU, and they'll render that. So you asked about procedural, which is kind of like what we're investing in right now with renderlet, heavily, is a continuous way of representing these surfaces. It's like, let's say you're representing a cylinder. Right now in like 3D graphics, if you need to render a cylinder, you would write an algorithm to take slices of it and turn those slices into polygons. So like, let's say 18 discrete steps around a circle, you turn those into 18 little line segments, and then you generate those. I'm drawing with my hands. You can't see what I'm doing.
Well, the people on YouTube can, but he's making a cylinder with his hands.
I'm making a cylinder with my hands. So you can imagine there is a discrete representation that is an approximation of an actual cylinder. So very simply, procedural space is keeping the design intent behind that. So we're going to use code to represent that instead of those polygons. And so let's say a procedural object for a cylinder is just a radius and a height, and that's it. That's the data structure. And then the interpretation of that is kind of left up to the viewer. So you could ship your data as that, and you could write a function that iterates over that and generates polygons like we talked about, or you could, let's say, do a continuous rendering like a NURB surface, or there's a lot of tools that have come out. There's even one from Adobe called Project Neo that are working on something called SDF-based rendering, which is a more continuous volumetric representation of the surface. And so there's tools for this today. There's software like Houdini, which is a node-based system. This is how they do a lot of effects in movies and films, and it's been around forever. There's domain-specific procedural design tools. There's like City Engine from Esri, which is a tool for generating 3D buildings, for example. There's, let's see, what else? Even in traditional game engines, I mentioned Unreal Engine before. It's got something called the Procedural Content Generation Toolbox, which is kind of a portion of that engine. And even Blender as a 3D editor has something called geometry nodes, which are a framework for doing a lot of things we just described. So where this all applies to renderlet and why we're investing so heavily in this right now in our initial version is we can take what we call a procedural system, which is the series of math effectively that represent shapes. We can compile those to Wasm functions. And so with that, we have a very powerful high performance construct where you can run those functions at runtime. And we can do this much faster than any procedural runtime that exists today, both due to the power of Wasm and also due to a bunch of optimizations that we put in to the system as well. And so you can run these procedural systems in an editor. You can take that and export it as Wasm code, and the exact same stuff runs in your application as well, like in your game or in your plugin or in your CAD tool. You can distribute these just as Wasm modules and plug them into an application, no code required. And it can even be generated by AI because you can train AIs on procedural grammar. So to us, like if we go back to the one of the very core concepts of the talk, which was the DevX experience for graphics is kind of terrible. We think we can solve that DevX by having that same chunk of code available and easily graphically edited in an editor, shipped at runtime, generated, safely distributed.
So I think the first time I've seen something like this, and correct me if I'm wrong, is maybe Microsoft Flight Simulator that allowed you to use
Yes.
WebAssembly, and then you provide your whatever landscape data, which I guess is also procedural, so it can be generated on the fly. It's not as big as, do you say raster graphics in 3D? I have no idea. So like essentially you just describe what you mean, as you said before, without losing the concept. But like, again, sorry, and I have to say, again, I'm not an expert here. So doesn't this problem already have a solution? So if you think Photoshop, they mentioned that before, we have a canvas in HTML, you have some WebAssembly code that runs somewhere, does a computation, and then spits out the pixels that get drawn onto the canvas. We have an article written by Ingvar Stepanyan, who used to work at Google, who describes how to connect Scripting with the canvas. There's Google Maps, there's Figma. So the concept seems like well established. So how do you think there's room for more? And yeah, what is it that you do differently than those solutions that are well established on the market?
Fantastic question. First, on Flight Simulator, I want to give that team a shout out. I know Jorg Newman, Microsoft, and the whole team at Adobe very well. And that is a great example of procedural designs. They had kind of built a procedural representation of large portions of the Earth, both in terms of buildings and in terms of like landscape. Like I think they do this thing they call runtime pixel shader detection. So they'll take like imagery of the Earth and they'll run a little algorithm that says like, is this grass? And if that pixel on that, like Google Maps style imagery represents grass, then they will put like 3D grass at runtime on that pixel in the tile. It's a super cool system. And I think where something like this is a little bit different is with that, it's built into the game engine, right? So that's code that they write and it works very well for them. But with this, anybody could write that code. I could produce an asset and put it on a store, or I could host it, on a third-party site, or stream it from some sort of data source and stream the Wasm modules back down to the app. And it kind of opens that ecosystem to any and all developers, and not just the authors of the first-party app itself. For Photoshop's a great example of kind of the graphic stack working pretty well in a browser. It was a long journey to get there, but it works very, very well today. It's, as far as I remember right, it's fully based on Inscripton. It renders to a canvas, just like an HTML canvas, the actual image internals, backed by WebGL, and then kind of the surrounding Chrome, all of the panels and buttons and all of the UI elements are rendered with a JavaScript UI library as well, and there's some interaction back and forth between that. So it's it's pretty high performance. There are still some performance limitations, and it works pretty well. But what I would say is that is a pretty specific use case. I think that does work well for Figma or for Google Maps or for Photoshops of the world. But I think it's not as general a purpose of a solution to all applications as you might think. I don't know, Mindy, I'm curious for your thoughts on this as well.
Right. Yeah. So first of all, that's Inscription specifically is like C and C++ specific, which works great in that case, but it's not general purpose. There are some potential performance implications there. You do need to do at least 2 copies when doing it through that system. You don't have access to like newer GPU features. And there are other features that we can provide outside of the browser that simply don't make sense in the browser. For example, serverless workloads, maybe pixel streaming. So the way xCloud works, where they render everything on a server, and then you can have like a very low end device that streams a video of the UI. And imagine being able to do that serverless. That's pretty cool. And just general out of browser apps, all those cases are not covered by like Inscription, which is very browser specific.
Understood. So you mentioned WebGL. You also mentioned WebGPU. I guess in general, the future is the future of WebGPU. But it's still a relatively young standard, and I think still in development. So my colleague Francois Beaufort, he has this running series of what's new in WebGPU, and there's always something new each Chrome release. I think Safari shipped it in technology preview, if I'm right. I think Firefox is working on it, but haven't shipped it yet. So it seems like a little early maybe in the hype cycle to base your entire company on top of a GPU. Is this a risky take that you're just happy to take, or is it is there more to it?
I think it's a calculated risk. I think WebGPU has been a bit of a controversial technology. Just to sum up many years of history that, as Francois, there's been a lot more history than I've been privy to. I've just been working with it for the last couple of years. But started with like things like GL Next, trying to bring compute shaders to WebGL. I think kind of morphed into what is WebGPU today, around 2019, 2020. I think the design, there's various aspects of the design that have been maybe a little controversial. For example, the syntax for the shader system. To your point, it is still it's a technology in its infancy, right? But I think a lot of the rough edges around the design have been solved. I know it's not officially a W3C standard yet. It's still a working draft, but I think it is extremely close to becoming a standard. And regardless, I think the feature set for, let's call it V1 of it, is fairly stable at this point. So I think there are some technical things that the Firefox team is working with in coordination with the WGPU team right now in order to get it enabled and get everybody across the finish line with it. But I think I think it is a real useful technology. I think it is the best cross-platform graphics API, and I don't just mean in the web browser. I just mean period that exists right now.
Yeah, we've seen the Dino project. They implemented WebGPU as well.
Yeah, exactly. And so there's in just an audience for the an exercise to the audience is you can look up some of these things like there's Dawn, which is made by Google, and there's WGPU, which is kind of an independent open source project. These are the WebGPU backends for Chrome and Firefox, respectively. And these are things that obviously are part of browsers, but work as graphics engines just fine as standalone systems as well. So tools like Dino can plug into them very easily. I think, look, I think WebGPU is the future, and I think the future is basically here now. And I think this is especially relevant to us as we're working kind of, outside of a browser, because we are not kind of subject to, we still want some of the same security guarantees that Wasm gives us, but we're not subject to kind of some of the same, hardening of the web ecosystem, let's say, and integration with all the other web technologies as well. Um, so let's see. I want to make sure I cover because I strongly believe in the future of WebGPU. I want to make sure I cover all the points about why I think it is a great technology to build not just something like this, but kind of the future of graphics too. I think I think performance comes up. I would like to talk about that. I think standardization comes up, but I think we're basically there. Deployment comes up. I think we're also basically there, and I think that is just unfortunately a little bit more relevant for web browsers than us at the moment. I think features comes up some too. I think there has been kind of a push towards feature parity with native graphics APIs to the degree that's possible at this point. I do think things have kind of slowed down for a bit, just with the impending V1 release, and I think there's the intention to add kind of new like post V1, post MVP, new sets of features regularly that developers can opt into, or new devices or new browsers can enable. There are specific features we need in renderlet that are not necessarily part of the spec right now, but we see progress on all of them. One is draw indirect count, or I think they're actually calling it multi-draw indirect in the spec now. Kai from Google actually has a prototype of this that's in Dawn today, so you can use this with a flag in Chrome today. This allows you to do something called GPU-driven rendering, which is where, let's take a step back and you think about all that Wasm code that we're building that's configuring the graphics pipeline. With that, you can actually shift some of that logic onto the GPU itself. So you're decreasing even more the amount of work the CPU has to do. Mesh shaders are kind of a newer technology that are very important, and this just changes how the vertex rendering pipeline works. I think these are important. They haven't seen as much adoption in games, I think, as some people would like. It's kind of a newer technology, but they will also enable us to emulate features that are missing in WebGPU that are present in desktop graphics APIs, and that a lot of older and even up until recently, more modern games use, like geometry shaders, for example. And then I think last, this is the most relevant to renderlet, is something called work graphs, which is a very new technology. But this allows you to do node-based rendering on a GPU and output compute shaders or vertex data from that, as well as mesh shaders. Word soup, I know. But very simply, what this means for renderlet is these procedural steps, these procedural functions right now that we're writing on the CPU, or pushing to a compute shader in an inefficient way, we can shift that fully to the GPU. So then there's still WebAssembly involved, but the configuration of the pipeline is extremely minimal. It's almost akin to, I don't know if you've had anybody talk about on this podcast before, but something like wasi-gfx, where the Wasm code is responsible simply for configuring stuff, and all of the actual computation happens outside of Wasm on a backend library. That's the goal for us. And so I think, to summarize, like, I think the future is now. I think now is a great time to be developing applications on top of WebGPU. it's maybe not quite there yet in terms of standardization, but in terms of stabilization, in terms of its future prospects, it is the future.
If I can just add about the riskiness of WebGPU, I don't think it's that much more risky than WebAssembly itself. Browsers have largely agreed to the technology. They are still working out smaller details, but like the large API is mostly agreed upon. And the chance of it going away now is extremely low. Like all three major browser engines have implementations of it. And it's for the most part done. Like you can use it, it's usable. Even if it's like still behind flags because things are still changing a little bit. So I don't think it's actually that risky, and it's probably not that much more risky than WebAssembly itself.
Yeah, so I just wanted to ask from the perspective of a web developer, and for web developers, it's always like, how is the percentage of browsers that support a certain technology? And if it's not 99.99%, a lot of the big production sites of this world will be very hesitant to use something like a new technology. I wanted to ask about performance a bit again, because you have the native way of talking to the GPU per operating system. Then you have WebGPU, which is an abstraction on top of that. And then you add another abstraction in the form of WebAssembly. And you mentioned sandboxing, which I guess is always in conflict a bit with the maximum performance that you could get. So how do you still achieve enough sufficient performance for doing the renderlet rendering that you want to do, and still get accepted good frame rates?
Great questions. I think there is a lack of high quality benchmarks that go fully end to end in these kinds of graphical applications. So I think performance gets talked about in broad strokes, and it's actually very nuanced. And we have found that two things, both on the WebAssembly and WebGPU side. On the WebAssembly side, specifically for CPU-driven code, like SIMD optimized, the kind of stuff you do in graphics. And I've said this number before, and this number still holds. It is highly workload dependent, but we do typically see about 80% of native execution speed in WebAssembly that we see in raw native code. And for us, especially as we move more towards GPU-driven rendering, that's an acceptable number. Because the idea is we don't have, and maybe this is a little bit different from like a super high performance game where every frame matters. We don't have a extremely hot loop that's managing, 12 gig of VRAM and, 32 gig of RAM on your system and, paging assets from disk and streaming assets from internet, all this stuff. Like we don't have that like single hot main loop. And so for the kind of operations we're doing, it's a little bit slower, but also like because of the different programming model, it works just fine for our use case. On the web GPU side for performance, I am not an expert here, and I'd be curious from more expert take and more users take as well. Our experience has been that performance is pretty good across the board, and a lot of that does go to optimization. A lot of that does go to the shift towards GPU-driven rendering just through compute shaders as well. There is a specific performance problem in the nexus of WebAssembly to WebGPU that we are tracking, and we've been working with Chrome folks and people at Google and people in the community as well on. I think that there's some solutions to it, and very simply said, when you're working in a Wasm context in a browser and writing like streaming large amounts of data to the GPU, effectively that has to go into Wasm linear memory first, and then get copied out of that from the JavaScript side into WebGPU accessible memory, so it ultimately gets uploaded to the GPU. So very succinctly, there's an extra copy in there that we'd like to get rid of, and it's just because of the structure of WebAssembly being backed by an array buffer. There are a few potential solutions being thrown around. I think DT, who you've had on this podcast before, is the champion of a proposal called memory control, which effectively adds mmap to WebAssembly. And so with that, you could just map, still balance check on the host side, that you can map ranges of native heap memory that is GPU accessible selectively into WebAssembly for the guest to write into. I think Luke Wagner, who you've also had on here, is championing various streaming-based approaches where you can have a persistent stream or a temporary stream that's open to channel data, and there might be some performance optimizations we could do there as well. So yeah, very specific problem. We'll put in the show notes some of the links to some of those things in there. But the only thing I'll say is for renderlet specifically right now and for wasi-gfx, this is not a problem because we can optimize that copy already outside the browser because we're not backed by an array buffer. Yeah, I don't know. I don't know if you have anything to add, Mindy, but our experience has been like for most use cases, performance is good, pretty good.
Yeah, that's great to hear. So you mentioned the word championing twice, which is a good segue into the next question that I had. So you two are the champions of a proposal called wasi-gfx. You're giving a talk at WasmCon about this. We'll link it in the show notes, of course. WASI, the WebAssembly system interface, and GFX for graphics, I guess. So there's different components of this proposal. There's WASI WebGPU for interacting with GPUs. There's WASI Frame Buffer. You just mentioned Frame Buffer a lot. Also, there's a CPU-based graphics API for that. There's WASI Surface, which is, well, a surface. And then there's WASI Graphics Context, which, according to the document that you have on GitHub, is a small interface connecting the graphics API, in this case WebGPU or a frame buffer, to the surface. So can you talk us through the wasi-gfx proposal and the various WASI:* subcomponents of it?
Yeah, for sure. So first of all, I'd just say that this is like an open standard. This is not specific to renderlet, even though we're making heavy use of it. So there are 4 packages there, yes. One is WASI WebGPU, which is like the bulk of the work. It's bringing WebGPU to WASI. The other ones are mostly are smaller things. So WASI Frame Buffer is if you just want a frame buffer to render to, you can do WASI Frame Buffer. So you choose either WASI Frame Buffer or WASI WebGPU, and that's just going to let you render. But actually getting it onto the screen, for that you would use WASI Surface. So on the web, you would basically connect the WebGPU or something else like WebGL. You would connect that to a canvas. Since we don't have canvas in WASI, that's why we have WASI Surface. It is a very basic surface that you can simply draw to with either WebGPU or a frame buffer API. And graphics context is just the point of connection between, on one side you take the surface, and the other side you take either a frame buffer or WebGPU, and you connect them through that way. The reason we have this intermediate step, the graphics context, is to allow newer graphics APIs or newer windowing APIs in the future, and they shouldn't be dependent on each other. On the web, everything is dependent on canvas, but in WASI, you're not expected to always have everything available. You can just pick and choose whether your runtime supports. So that's why we have the intermediate step that just takes whatever you want. There is potential there to develop a full windowing API. That would be really cool, but also takes an enormous amount of work. So we're not doing that for now, but maybe someday.
So this is a bit of a sidetrack question. I apologize for that. But I know that a lot of people are really interested in connecting the worlds of WebAssembly and the world of WebGPU for the reason of AI. So in this particular space, so you obviously don't even need a surface, you don't need a canvas or anything. You just are interested in connecting the GPU cores with whatever powers your WebAssembly AI logic. Is this something that WASI WebGPU can help, and maybe even in the browser?
Yeah, absolutely. And if you don't connect the graphics context, it simply won't have access to graphics, and you can do all the compute things with it. This has a lot of potential for, especially for cases like serverless, where this is a common use case. You want to do some AI workload, but as of now, you probably have to use some sort of proprietary API for that. But if this would let you do it in a general purpose way, just get access to GPU, run in your AI workloads, and get your result.
Interesting.
I'll add to, I think we mentioned this a little bit in our talk at WasmCon. There, for outside of browser so in browser, people are doing interesting like AI and ML things with WebGPU today. Outside of a browser right now for Wasm, wasi-NN is kind of the solution to that. And we view ourselves as being kind of complementary. And so wasi-NN effectively supports a few different ML backends, like allows you to configure them, load some weights, and then run inference. So if you're doing like non-inference things, that's something we can do with WASI WebGPU specifically. And but even more generally, we can allow you to take some of that maybe like browser-based WebGPU-based AI frameworks and run that directly on WASI WebGPU. And we think that WasmAssembly could even be implemented in terms of WASI WebGPU with the GPU backend. So shifting some of that logic back into the Wasm stack, but keeping performance parity. So the two both exist for a reason, and they're largely complementary approaches.
Yeah, so on the NN space, there's WebNN as an API that is also in development right now. So there might be some interesting wasi-NN powering WebNN in the end, just like wasi-gfx connects to WebGPU in the future or now already. So that's an interesting connection. They're talking of connections. So the way you made the WebGPU bindings work is, if I understand correctly, you have taken the WebIDL, so the web interface description language, for the WebGPU operations, and you have mapped those to WIT, so WIT as the Wasm interface type format. And looking around in your repository, it seems like you have even made this idea more generic, and you've written something called WebIDL to WIT, so taking any WebIDL to then map it to WIT, which in the end would allow you to create bindings to WebAssembly from any JavaScript API, because all of the JavaScript APIs are described with WebIDL. What are your plans there? Why is this just something you could do because you had the logic sort of already lying around, or are there any concrete plans for like more things that you want to do with this?
Yeah, great question. So we started obviously with the WebGPU, but as people saw it, they started to think that maybe in the future we might want to use it for additional APIs. And so that's why we built a tool in an independent way. But we also have a different project, which is not officially part of renderlet, but it's a project that I've been doing on my side with a couple other people. I call it for now browser.wit. And the idea is to bring all of the web APIs, not through WASI, but to the component model. And the component model is a building block of WASI. WASI is built on top of the component model. And the component model gives you high-level interfaces to interact between languages, between the host and the guest, or between guests. So using that same component model, we built browser.wit that gives you access to. The goal is to have all web APIs in Wasm. It's not native, but it's like very close to native, and the glue code is fairly small, much smaller than existing solutions that most languages have, and most languages, the solutions in most languages are also language specific. We're trying to do something that works across languages. It is not yet ready to use. Shout out Calvin Prewitt, who is doing a lot of groundwork to make this possible, enabling. He's working on async in a different project called Jaco, which I think has been mentioned in this show in the past.
It was, yes.
Yeah, so that's some groundwork that is needed in order to make this actually usable for like day to day. But yeah, the goal is to have all web APIs in Wasm without a lot of glue code, with a minimal amount of glue code.
Yeah, so as a web developer, that's something that's very exciting to me. I looked at Kotlin Wasm, for example, and they sort of just re-implement all of the web APIs as native Kotlin code. So you have document query selector and stuff just in Kotlin form. I guess there's something similar for Ruby, where you can create actual DOM with Ruby functions and so on, and just a remapping of those APIs. But having this in a language agnostic Wasm component model representation, I guess, is a good word for that. This sounds like a very powerful concept. I'm pretty interested in keeping an eye on that. And I will definitely ask you again to come on the show once this is something that you can actually play with.
For sure.
We have been really diving deep into some of the topics, and I have to admit some of it was above of my head, but there's the show notes, so you can always dive deeper, and if you're interested, just go to the show notes, check the talks that Sean and Mendy have given. I wanted to ask on a bit of a lighter note at the end, what are your plans with renderlet? Do you want to become like something like the jQuery of graphics with WebAssembly, or do you want to open source everything, and do you want to close source everything? So far, looking at your repo, there's a bunch of things, like the playground is not open source yet, but we've seen it in the talk and so on. So what is the future there?
Great questions. I would almost invert that a little bit. I would say, and Mendy, keep me honest here. I think wasi-gfx and this ecosystem we're building around graphics for WebAssembly should become the jQuery of graphics in Wasm. Look, we're heavily committed to open source, and like what we've built is very general purpose, and we think could be used for a lot of applications. And so I think seeing that continue to grow and maybe grow on to become, not just a standard in the like we're W3C standard kind of way, but actually become the standard like jQuery, the thing that developers look to. I think that's an awesome goal for that. I think for renderlet itself, we want to be building tools on top of it, right? And we will open source some things, but I think some things will also stay closed source, and that's fine. Particularly things like editors, like what we're building to replace the playground today, will probably stay closed source. But specific libraries, specific utilities, we will always contribute back to the open source where there is broader applicability. The direction for renderlet, like I talked about all the procedural design stuff earlier, and that's what we're heavily building right now. We'll have a product to announce later this year that is centered around that. So please sign up for our wait list. We'd love to get in touch once that's ready. But more generally, where we want renderlet to go is to address all of these things that I talked about in that very first talk, where we think there's a better way to do 2D and 3D graphics. Right now there's game engines, and there's libraries like 3JS, and there's kind of these domain-specific solutions. We want to be the general purpose 3D and 2D graphics engine that just works anywhere and works with any app out of the box. And I think it's a crazy large vision, but I'm excited to see where that goes.
It almost feels a bit like, is it Wallace and Gromit? This meme where there's, is it Wallace is the dog or Gromit is the dog? Like, anyways, the dog is on the train, and he puts the tracks as the train is driving. It feels a little bit like that. With you're building the standard with wasi-gfx. At the same time, you're building the company that is using the standard. So good luck with that, and I'm very excited, and I am pretty sure you can make it happen. So Wallace and Gromit brings us to the last part of the show, which is Wasm, but not. So for you, when you instantiate streaming on any of your streaming devices, what is it that you're currently watching or listening to? And can be Wallace and Gromit, who knows? Who wants to start?
I'll let you go first, Sean.
Okay, I'll go first. We watch lots of things on streaming, but my guilty pleasure is HGTV, or just home renovation shows in general. I live in a beautiful but tiny New York City apartment right now. Dream of having that house someday, and I know exactly how I'm going to design my kitchen and bathroom when I have that.
Nice. And as he was saying that, he was turning around. There was just a white wall visible. So it must be a really tiny apartment.
It is a beautiful, and is an apartment, and is bigger than I thought. And I'll show you briefly the beautiful sunny but cold day we have in the background here in New York City. Right. Yes.
Awesome. Mendy, what about you?
Yeah, I'd give a shout out to two of your former colleagues, Jake Archibald and Surma. They have a great show called Of the Main Thread. I think when they were at Google, it was called HTTP 203. And I love that show. I have listened to most episodes more than once. So it's a really great show. And I learned a ton from them.
So have I. I'm a great avid listener of this show as well. Yeah, so Jake and Surma, if you hear this, you have two fans out there, Mendy and I, and I'm sure many, many more.
For sure.
And then the last question is local get and global set. So if you can local get something and globally set it onto the world, what would it be? And then you can inverse it. And I asked you, because you're two on the show for the first time, that one answer the question in the one sense and the other person answer the question in the other sense. So local get global set or global get local set.
So I guess I'll take the local get global set. I would like more people to sign up to the bone marrow donor registry. I've had the honor to be a donor, and it was a lot easier than people think, but it's also really hard to match people, and some people just simply can't find donors. So especially if you're like from a minority or a mixed race, that's really important that you sign up. You are very unlikely to actually be called, but you'll know that you have done your part. And if you do get called, it's not a big deal. It's basically a long blood test, essentially. So yeah, I think more people should do it.
Awesome. Yeah, I'm a donor as well. I haven't been called yet, but it's great to hear that actually someone needed yours. So that's great. Sean, what about you?
Okay, so I guess that leaves me with global get local set. Continuing on that same theme, uh, you know, Mindy and I are based here in the U.S., and I would say our healthcare system is probably the most expensive in the world, and also has pretty terrible outcomes compared to high income economies. Like, I was reading a story the other day that said we're 34th in life expectancy. So if we were to learn something from everyone and apply it, it seems like a lot of other people in the world have figured out this healthcare thing. I'd love to see this become a solved problem here.
I'm not American, but I've heard it from many Americans that there's leaves to be desired. So I would just leave this uncommented. The American says so. And I guess, yeah, that's maybe something, but yeah, I should stay neutral here. We have great health coverage here, so I'm definitely happy that I don't have to worry about this. Cool. So people wanting to follow you, Sean, Mendy, or Renderlet, the company, how should they do? Do you use social media? Do you use LinkedIn? Should people email you? You mentioned the wait list for the company. So what's ways for people to stay in touch?
Great questions. Yeah, if you want to sign up for the waitlist, just renderlet.com. Just give us your email address. We don't need anything more. Happy to let you know when we have some exciting news. I'm not. I need to be better about social media. I'm not a big social media person, but I'll put in the notes. I am still on Twitter, for better or worse. The Isomizer is my handle. Connect with me on LinkedIn. Just Isom, my last name. Also, I'm old school. Feel free to send me an email. It's just Sean@renderlet.com.
Awesome. How about you, Mendy?
Yeah, I'm not super active on social media. The place that I use that I'm the most is probably Mastodon. So I'm at Mendy at mastodon.align. I'm also on LinkedIn if you want to try to reach out there, but I didn't check it very often.
All right. So we will put all those contacts in the show notes. Thank you very much for listening, for watching this. It was a complex episode, so also definitely check the show notes for the links to the talks. If you go to Barcelona for WasmIO, I think it's March that the conference is happening. So
27th and 28th.
all right, there you got it. Be sure to catch Mendy and Sean in person. And with that, if you have something interesting to say in the WebAssembly space, definitely do reach out. Tomayak on all social media, on email, on everything. Tomayak, you will find whatever social platform you want to reach out to. And I'm super old school too, so I'm just reachable via email as well. So thank you very much for listening, for watching. Mendy, Sean, for being on the show, for explaining us all those super complex graphics concepts. And with that, yeah, I see and listen to you next time. Bye-bye. Thank you.
Thanks, Tom.
Thanks.